Now we'll start talking about the solutions to polynomials over the ring of p-adic integers. If f is a polynomial in m variables over the ring of p-adic integers, and if n is a positive integer, we denote by f sub n. The polynomial is coefficients in a sub n, deduced from f by reduction. Passing from zp to an, this is a reduction modulo p to the power n. So for a polynomial with coefficients in zp, we'll throw those coefficients into a sub n, which is z mod pnz. And the resulting polynomial will be denoted by f sub n. And now we can state our first proposition, that f superscript I, where I is an index. In case some people may get confused, this is not the i's derivative. Let f superscript i's be a family of polynomials in m variables over zp. The following two statements are equivalent. The first statement says that this family of polynomials have a common zero in zpm. What I mean by this is the Cartesian product of zp's, where there are m factors. And the second statement is that for any n bigger or equal to 1, the polynomials f superscript I sub n have a common zero in ANM. And here, this is given by the definition here. This fin is a reduction of fi, where the coefficients of fi, which are originally in zp, are reduced to an by modulo pn. And also in Sayre's book, this is stated as n strictly bigger than 1. But I think that is a typo. It should be n bigger or equal to 1. Now let's prove this. The proof is based on this lemma, where the existence of the common zero will be translated to the non-emptiness of the projective limit. And those d sub n's will correspond to the common zeros for fins. Specifically, let d and respectively d sub n is a set of common zeros of the fi's and respectively fins. We are going to make the following claim. We claim that this d is precisely the projective limit of dn's. Why is it so? The verification is straightforward, but the notations might look a bit messy. So we have to be very careful with the notations. Indeed, By definition, Dn is a set of common zeros for Fins. This is Dn. And now, by definition, what is the inverse limit for Dn? The elements here will look like x1, xm, where each x of I is an infinite vector. And we still have this, except that now we are going to look at the nth components of this. This is for any I and any n. Also, for the inverse limit, we need a compatibility condition. And that is represented by this equation. And here, you can also write this thing as the infinite product of an m-fold Cartesian product. You can first take the m-fold Cartesian product, then take the infinite product. They are actually the same. And each vector xi has its ith component denoted by x of in, which is what's going on here. And now let's write down what D is. The set D is a collection of elements x1 through xm, and this is in the m-fold Cartesian product of Zp. And this is a common zero for Fis, which means Fi of x1 through xm is equal to 0. And I also need to emphasize that this happens in an, and this is also happening in an. But this happens in Zp. And now let us see why this D is equal to the project limit of Dn's. Because Zp, each Zp is a project limit of An's, and each xi is in Zp. So each xi satisfies the compatibility condition. Putting all of those compatibility conditions together, we get this equation. And now, let's see why this condition for any I, any n is equivalent to this condition. I forgot to add that this is for any I. Given a fixed I, why this true for all n is equal to this? So let us just try to convince ourselves that those two shaded statements are the same. That these two statements are equivalent is just from our definition here. Because if you just compare the left-hand sides, you will see the left-hand side here is a reduction of the left-hand side here. by passing from Zp to An through modulo Pn. The coefficients here are from the coefficients here through this reduction, and those x sub i's are also reductions of xi's here modulo Pn. So those two shaded statements are equivalent. And we have verified this claim. Now we can use our lemma. Since A sub n's, which are z mod p and z's, are finite, and therefore d sub n's are also finite. And now by our lemma, this is on page 13 of Sarah's book, the projected limit of d sub n's is non-empty if and only if d sub n's are non-empty for any n bigger or equal to 1. So this is bigger or equal to 1. That is why I believe that there's a typo in Sarah's book. It should be n bigger or equal to 1. And this completes the proof of the lemma. Next, we are going to make a connection to the field of p-adic numbers. For polynomial equations with coefficients in Zp, we are also interested to know their solutions in the field of p-adic numbers. And the next proposition will give an answer for homogeneous polynomials, meaning the polynomial whose all monomials have the same degree. But before we talk about that proposition, there is an important notion we need to introduce, called the primitivity for a vector in Zpn. A point x with m components in Zpm. Here each xi is regarded as an infinite vector or compatible sequence in Zp. And this x is a vector with m components. And this guy lives in Zpm. The point here is called primitive. If one of xi's is invertible in Zp. That is to say, if those xi's are not all divisible by p. And of course, here one of really means at least one of. So to avoid confusion, let me just write some. And one can also define in a similar way for the primitive elements in ANM. An element in here is invertible if at least one component is invertible in the corresponding AN. Now we can state our next proposition. This proposition is also about the equivalence of multiple statements. And this time, it involves QP, the field of p-adic numbers. But the little price to pay here is that the polynomials we are talking about here will be homogeneous polynomials. Let f superscript i's be a family of polynomials in m variables that are homogeneous. Recall that by homogeneous, we mean each polynomial consists of monomials with the same degree. This is a representation of f super I in terms of monomials in complicated notations. So the sum of R1 through Rm for each monomial is always equal to the same integer, some d super I. Then the following statements are equivalent. Part A states that the FIs have a non-trivial common zero in QPM. Part B says that the FIs have a common primitive zero in ZPM. And part C says for all n bigger or equal to 1, FINs have a common primitive zero in ANM. Proposition 6 says that those three statements are equivalent. Now let's prove this. By definition, the trivial zero for FIs is not primitive because 0 is not invertible. And ZP is contained in QP. We know that B implies A because if we have a common primitive zero in ZPM, then that common zero cannot be the trivial zero. And that zero will become a non-trivial common zero for f super i's in QPM. So B implies A. Now on the other hand, if we have a non-trivial common zero of FIs in QPM, under the statement A, then we put H to be the smallest integer among the p-adic valuations of x1 through xm. And we put y to be p raised to the power negative h times x, which by definition is p negative h x1 dot p negative h xm. This y is still a common zero for all FIs. Do you see why this is true? This is true because of homogeneity. If you multiply each x of I by p to the negative h for this given h, and you factor all of them out, you get the same power of p for all monomials. If you want to write this more carefully, we'll pull out all of those p to the negative h's out. We'll get p raised to the power negative h times r1 through rm, which by homogeneity, the sum is always equal to d super I. So this is equal to p to the power negative h di times fi of x1 through xm. Therefore, if x is a non-trivial common zero for fi's, then this y is also a common zero for fi's in QP. But by our choice of h, this y is not just in QPM, it is actually in ZPM. Why is y in ZPM? For this, we need to look at this definition more carefully. This is because h is the minimum of those valuations of x1 through xm. And now, if you multiply this x by this power, by the minimality of h among all valuations for x1 through xm, each component in its p-adic factorization will have a positive power of p after multiplying this by p to the negative h. And this y is not just an element in ZPM, but also primitive. Why it is primitive? That is because if, for example, this guy is the minimum, if h is equal to vpx1, then if you just look at p to the negative h times x1, by the p-adic factorization, you get p to the negative h times p to the vp of x1 times some invertible element u, and the first two terms cancel out, and you will get u, which is invertible. So because we have at least one component here that is invertible, this y is primitive. And y is also actually in ZPM, as I explained above. If you don't see that immediately, you can write down the p-adic factorization for x1 through xm, and you will see because h is the minimum among those valuations, all the p powers from the first component to the last component must be a positive power of p. So this y must live in ZPM. And this verifies this, that A implies B. And now let's see how B and C are equivalent, and then we are done. As you may have seen this, the equivalence between B and C look familiar to us because this is pretty much the statement for proposition 5. In proposition 5, we have shown that FIs have a common zero in ZPM is same as their reductions to ANs have common zero. So it suffices to show that being primitive here is same as being primitive here. So this equivalence follows from proposition 5, and this is on page 13 of Sayre's book. And the fact x1 through xm is primitive in ZPM if and only if their reductions x1n through xmn in ANMs is primitive for all n. This is not hard to see. Indeed, P divides xi in ZP if and only if P divides all components xin in an for any n. And that justifies the equivalence between the permittivity. Therefore, this verifies the equivalence between B and C, and therefore we have completed the whole proof.